Hey, everybody, this is going to be a rather lengthy lecture on exponentials and logs, but it's going to be there for you to keep looking at over the course of the term. And I'm not going to hold Algebra 1 students accountable for this as part of your grading. But my goal for you is to think mathematically, and everything's in place to get a full picture of things you're beginning to work with. So we're going to have at it. Also for homework, I'm going to put quadratics that you are responsible for graphing. And we've been at it now for, been graphing them for about 7 or 8 days. And I'm hoping that by midterm, everyone in this room will be able to correctly graph a quadratic. And I don't grade you till midterm. So you've got all this time to practice and one more step towards being able to get the idea. And so I encourage you to come in for Thursday night help. Practice it every day. When you come in here, it's going to be on every worksheet for the rest of the semester. And I'm hoping you have some success with it. All right, so let's have at it. I put things on the board instead of me generating them organically. I've thought about the process here and put all kinds of things on the board. So they're already there for us. Exponentials and logarithmic functions are inverses. Time to amount, time to quantity, quantity to time. Okay. Exponential models are in this form. We have a base, and the inverse has a base, right? And so I put B for base, and we're going to do the exponentiating, then some multiplying, and then some adding. So it would be nice if we could get A times 0 and K plus A times 1. And the answer to that is yes, we can. Now, the inverse is logarithmic, and I think we can see how to get that inverse. We've been practicing that. I could ask you to do that now, and hopefully you'd have some success. So what do we do if we're solving an equation? We've got an answer over here. What's the first thing you're going to do? Subtract K, then divide by A, and then know the inverse of B to the is log base B, and then division becomes multiplication. I'll put a little dot there, right? And then subtraction of H becomes addition of H. And whatever X gets you Y here, then that Y value, if it's a function and we're working with a calculator, we call it X, brings you back to what you started with. That's the process of an inverse. Okay, to make this simple, we have to understand something that we've been working on for 3 weeks. I think we started this on day 1. Okay, so we're looking at the top. So 5 to the x equals y. 5 squared is 25. Okay, nothing new there. That's called exponential form. Well, we can express the same quantities in logarithmic form. In a logarithm, we start with a y value, which in this case would be 25, and it gets us the x value, which is 2. And I think we've been practicing this in class. And in order to look at the activity on base 5, then you got to turn 25 into a base 5 statement. And maybe this helps you understand why I'm writing the number 2, because that's the exponential activity on top of 5. So let's look at m to the 5 over m to the 3. Yes, you're responsible for knowing that's m to the 2. How do we know it? Well, we've got 5m, 1, 2, 3, 4, 5. Those 2 times this 2, that might be something like 7 divided by 7. Well, I don't need to do that. I know eventually my answer is going to be m to the 3, because I'm dividing m times m out of the problem. So what's the exponential activity? Well, if I just look at the parentheses, it's m to the 5 over m to the 3 is, I don't know why I wrote that, I just wrote the same thing, is m to the 5 minus 3. Well, there's the exponential activity. So that's why that's answer here is a 2. I'm looking at the exponential activity, and I've got rules for that. Essential that we continue with looking at exponential rules here. All right, so what's the next thing? We've already established this. Right, and if you don't see how that works, you got to keep playing the video till you do. You can always plug numbers in for m. You can do 7 times 7 times 7 times 7 times 7 divided by 7 times 7 times 7. Well, I think I know that's the number 1. So 49 in that instance. Okay, but this is working for all numbers. So what about m to the 3 over m to the 3? Well, by definition, it's subtraction, and there's no difference. If there's no difference, then that means I have m to the 3 in the numerator and m to the 3 in the denominator, which means I'm dividing something by itself. Maybe that helps you understand why that's a 1. So anything to the 0 is 1. Why is that important? Well, I'm going to get to that question next. Maybe I can show it here and everything. Why is it important? I mean, that's really what I just said, right? Because functions have a little multiplication in them and usually a little addition, subtraction. And what are the easy numbers to multiply by? 0 and 1. If this was 0, then my y value is c. If this is 1, then my y value is m plus c. And I don't need a calculator to see that. And so let's try to replicate it. Let's try to use that information. So again, m to the 3 over m to the 3 is 3 minus 3. That's another way of writing that. 3 minus 3 is 0. So what do I put on top of an m to get m to the 0? 0. So what do I put on top of m to get 1? Well, that's something divided by itself. There's no difference in the number of factors. No difference. None. Same number. Exponent, numerator, denominator, no difference. Means something's divided by itself, it's 1. All right, so let's get after it. Let's see if we can write these equations as quickly and easily as we write the equation of a line, which people are starting to do correctly. Okay, that's good. I've had students graduate from Algebra 2 in the early 90s that couldn't. Six kids in Algebra 2 in a class I had, which was the same as everybody else's class, couldn't write the equation of a line. Well, got to do something different, right? And that's why I got away from sequential education. All right, so k plus ab x minus h over d. Back to that general form. I think in the textbooks you'd see ab to the x plus c, but they can get more complicated, so we're going right there from the get-go. All right, so what would it be nice? It would be nice if I could make this k plus a to the b to the 0. Because I know that answer. B to the 0 is 1. So this is k plus a. Well, that's a lot simpler than the way it's written on the left. And I got k plus a b to the 1. Well, that would be nice because that's just k plus ab. Right? Simpler. A little bit simpler. One of the things we want to learn in math is to make problems simpler. I think that transcends disciplines. Right? So how do we do that? Well, I want a 0 and a 1. And why don't I do x minus h over d equals 0? And why don't I do x minus h over d equals 1? And let's get ourselves a little xy table here. Well, I know when it's 0, I get k plus a. Well, how do I make this fraction 0? I guess it's got to be h. All right, the only way you can have a fraction 0 is to have 0 in the numerator, right? Because if you have 0 in the denominator, that's undefined. We'll talk about that more as we move forward. All right, so how do I make this number 1? Well, I think I got to multiply by d and add h. Oh, geez, if I get that number, I can just add something real quick. And if I do, I get k plus ab. All right, now remember, you're not going to get this immediately, just like you didn't get any of the problems we started with. Remember, the median for the first test was about 4. Testing again today, I'm hoping that number is significantly higher. And rather than linear progression, I'd like to see some exponential growth. That's going up faster. Okay, so what about so over here now, I'm kind of running into, I'm going to erase that, right? Because now we're going to do the inverse. All right, and we did the inverse over there, I think already, in terms of moving k over minus k, dividing by a, log base b, multiplying by d, adding h. So that's what's over here. And I guess I got to use, if this table is moving easily. Not quite, so I don't want to drag it. Oh, that's worse. So that one's got to be up. That one's got to be up. The ones in the back have to be up. And this one I think is down. Up, down, it's up, and I can't get that one, but that's moving better now. All right, so if b to the 0 equals 1, and I am going to try to do the inverse, then I got to start with a 1. Oh yeah. So log base b of 1, we've established a 0. Why is that important? Because we're going to do some multiplication times these logarithms, and it's nice to be able to multiply something by 0. Do I have this centered? Okay, still going all right. Let's move this back a little bit. Don't want to say something and not have you not see me work with it. And what's the exponent you put on top of b to get b? Well, okay, that's b to the 0. So b to the 1 is b, right? And so what do I put on top of b to get b? A 1. And why is 1 important? Because we're going to do some multiplication. We want it to be easy. All right, so what can I say here? Well, the first thing I got to establish is just some numbers that you see. Minus 2 to the x, yeah, that's kind of awkward. You know, I can see squaring this gets me 4. Minus 2 to the 1 gets me minus 2. It's jumping all over the place. So this model, this exponential model, is based on b, the base, being bigger than 0. Okay, so we're going to do that first. We're just dealing with exponential growth in this video, just to get us started. But I'm going to look at 2 to the x. And I'm going to start with the number 3. 2 cubed is 8, 2 squared is 4, 2 to the 1 is 2. I wonder if you can fill in the table just by looking at this. Looking at the pattern. Well, I hope you'd say, how do you get from 8 to 4? Divide by 2. How do you get from 4 to 2? Divide by 2. 1, 1/2. 1/4. And yes, we've been practicing 2 to the negative 2, which is 1 over 2 squared, which is 1/4. We have been practicing that. And 2 to the negative 3, 1/8. And I'm asking the question, what are you heading to? I hope you can see that these fractions are getting smaller and smaller and smaller with movement to the left on the x-axis. And that's what asymptotic behavior is, because this is going to 0. Okay? So it's going to 0, and if we move in the positive direction, things are doubling. Every interval. Looking backwards, they're being cut in half. All right, just something to think about. We're going to develop our understanding of this over time. Can't do that until things are in front of us. So I'm putting it in front of you as something to consider. Just watch the video, put a smile on your face, and play it again tomorrow. And then play it again the next day. Play it again, Sam. All right, so where are we at now? We've established that there's what's called asymptotic behavior, which is a description of what's going on here. And the more I move to the past, the less I have. And I hope you can kind of see that. And if this one's 8, this one's 4, I hope you can start to see, you know, a ratio of 2 to 1. And that forms the base of these exponential models. So if this had been 12, then we would have had a triplet. Okay. Has to be said. All right, so how do I graph that quickly and easily? Because I could certainly move this thing down some units, right? I could move it down some units. It doesn't have to be built on top of 0. And that would have been 2 to the x minus 5. In a little different location when we plot it. All right. Doing okay on time. I still got to print out some tests for you today, and I have time to do it. So, on my YouTube channel, I do a lot of rapid fire how to graph exponential functions, and we want to be able to deal with this in what, 15 seconds. for you, for me, I hope it's a lot quicker. But we identify x as critical numbers, and you're trying to do that with a linear function, you're trying to do it with a quadratic, trying to do it everywhere. So what are the critical numbers there for x? Well, I hope you say 1900, and I hope you say 1950. And if you didn't, I hope you can see where I got those numbers from, and you're learning if you can make some gains here. So what happens when I put 1900 in? I get 7 plus 10 doubled to the 0. 2 to the 0 is what? 1. So I get 7 plus 10. Is that two numbers? Just like k plus a? Yup. And h? Didn't h make a 0? Okay. And the next number we find, we're going to get k plus ab. Okay. So k plus ab is going to get me times 2, provided I pick the right number. And I'm saying 1950. So 1950 minus 1900 is 50. 50 divided by 50 is 2 to the 1. Okay, so what do we have? Yeah, we got the k plus ab. So this number here is 17. Remember, 2 to the 0 is 1. Okay. And 2 times 10, 27. And how much did I go up from 17 to 27? 10 units. All right, so let's look at this from a graphical standpoint. I'll put all that information in there. So what do I see? Y equals 7 is that constant. So that's where our asymptotic behavior is going to come from. I see an initial jump of 10. And then I see a doubling of that, 20. Which means that this thing would be 40 next. And this one would be 5. And now I've got all kinds of nice numbers, because this happened at 1900. This happened at 1950. So this happens at 2000. And this one happens at 1850. Okay, so let's put 2000 in here. And we should get 40 on top of 7, right? I should have had y equals 7 written somewhere. All right, so 7 plus 40 means 2000 should get me 47 units. 2000 minus 1900. That's 100. Now, why is 100 nice? Because it's a multiple of 50. So 50 goes into 100 twice, which means I've got 7 plus 10 doubled twice. 4 times 10, 40 plus 7, 47. So that would have, this graph looks like this. And we've got all kinds of nice numbers that we can work with as long as we're changing by 50 years. Nice integer values. Of course, there's lots of other numbers there that a computer can tell you, you know, what it takes to get this or that. But right now, we're just trying to get a feel for what's going on. Okay. All right, so where am I at? So 47. 27 to 47 is 20. I can see this doubling. We don't want a linear mindset. That's what knocking people out of math at the pre-cal level, linear mindsets, because it's just one function of many. And everybody says, is it mx plus b? Well, it's nothing to do with mx plus b. Okay, so that's why we're giving you a little smattering of this and that, because you can't see patterns unless you're working with patterns. And patterns are all over math. All right, so what do we have here? We got a y asymptote on the left. We got a y asymptote of 7. We got ourselves 1900 gets us 17. We got 1950 gets us 27. And I'm saying that we have the inverse of this. So we want to see x equals 7 as an asymptote. We want 17 to get 1900. And we want 27 to get 1950. And how are we going to do that? We're going to do that by knowing something about log 0, log 1, and log b base b. Because I know the answer to this is 1. I know the answer to that is 0. And there's going to be multiplication. And I know that, you know, 2 to the x coming back to this How do you describe all the numbers on the 2 to the x? Did I erase it? Okay, I got to generate it again. Okay, this table again, 2 to the x, doesn't hurt to see it again. Repetition's our friend. Okay, 3 gets you 8, 2 gets you 4, 1 gets you 2, 0 gets you 1, -1 gets us a half, -2 gets us a fourth, an eighth. Oh, nice, right in between there. 160, great pass. Split 2 defenders. All right, well, how do you describe all the numbers on the y side? Because they're going to be the inputs here. They're all positive, which means x minus 7 over 10 has to be greater than 0. I should write that. It's got to be bigger than 0. Okay, so what makes that happen? What makes x minus, well, numbers better be bigger than 7. Okay, so x is, here's 7. I got to have numbers bigger than 7. And I want 1. Well, how do I make this thing equal to 1? I got to multiply by 10 and add 7. I guess I got to use the number 17. And if I put 17 in, I get this number, and 0 times 50 is 0. I get 1900. And then I guess I want the number 2 because I want, if that's the base, and I put a 2 in there, I can see I get 1. That's the exponential activity. So that exponential activity is 10 times 2 is 20 plus 7 is 27. And 27 minus 7 is 20. And 20 divided by 10 is 2. And what do I put on top of a 2 to get a 2? A 1. And 1 times 50 is 50 plus 1900 gets me 1950. And what number did I pick? 27. Well, those numbers should look familiar to you. I didn't draw this well. If I wanted to draw it well, then I do horizontal movement. 7 to 17 is actually 10, and I want 20. So I'd be double that, which is maybe right there. And I got a much better graph. These are in the way, but there's the graph of the inverse of the exponential model. All right, so let's just have me do a quick one. You play it several times if you want. I'm just going to graph this. So I want 5 plus 3 to the 7 tripled. And I want it to the 0. And I want 5 plus 7 times 3 to the 1. That gets me 2 points. Y equals 5 is the asymptote. That's the platform upon which exponential growth. I am going to jump 7. And then I'm going to jump 21. Because that's tripling. That's what's going on. So what do I pick? 2000. Gets me this equation, which gets me 12. 7 on top of 5. Tripling it gets me, what gets me a 1? Well, I got to add 25 to 2000. So 2025. Right? That's all I'm doing is making this thing 1. So I'm bringing 25 over and adding it to my initial amount. And that's going to get me that equation, and that's 21 plus 5 is 26. Okay, now I'm going to do the log. So what do if I'm doing a log? Almost done here. Hope I captured that over there. If not, play the video on how to graph exponential functions quickly. All right, so what makes a 0? A 5. Well, this has to be bigger than 5, but this isn't bigger than 5. I don't have any quantities. All right, on the left, we went time to exponent. Here we're going exponent to time, or quantity to amount. All right, so this is going backwards from time to bacterial growth. Well, this is the bacteria. There better be something there. So this thing has to be, and I'm going to start writing greater than. So I need numbers bigger than 5, but this calculation is undefined. All right, so what do? I do 7 times 1, 7 plus 5, 12. 12 should be a friendly number. That gets me log base 3 of 7 divided by 7, 1. Pushing that big time. Well, that's 0. 0 times anything is 0. That gets me 2000. So 12 gets me 2000. And then I want this thing to be a 3 because I know that answer. That answer is a 1. And 1 times 25 gets me 2025. I don't have the same inverse that I had over there. I don't think. Maybe I do. Maybe this is the exact inverse. Yeah, I guess it is. All right, and so now, what's the last thing is to get the year, I'm sorry, the amount, okay, and the amount is using the, okay, where am I at? I want a 5, I want a 12, and then I want the same base, so 3, 21, 26. Okay, oh yeah, now I can see the 7 change and the 21 showing up there. So 26 gets me 2025, and with more time, that's what you get. Which means that we can take the graph and think backwards and very quickly write exponential models. So 8, everything is where? Above it. How much is 11 above it? 3. Next time it's not 3. How far is it from 8 to 18? 10. So I got a little bit more than a tripling function. I'm going to make a 0 out of 2000 and 25. Elapsed time. I can do the same thing over here very quickly. I can take the year 2000. You see this? We get a little closer. What's this graph? Well, I got 2000. How do we get from 2000 to 2025? I got to add 25. I know this is the shape of a logarithmic curve. I've got to be bigger than 10. I better say x minus 10. Things have to be bigger than 10. How much bigger are they? 2 units. Right? So now if I put 12 in, I get log 1, which is 0 times anything is 0. It works for that, and it works for that. Just got to put a 21 in. 21 minus 10 is 12 divided by is 11. 21. If I got that number right here. Where's the, excuse me. So I just have to plug it in. I just got to plug it in, whatever I get. So these are not inverses, obviously. Okay. 21 minus 10 is 11 halves. If you make this 11 halves, then you have log 11 halves, base 11 halves, and I hope you can see that as a 1. That's the exponent you put on top of that to get that. Why is 1 good? Because you're multiplying it times 25. You're adding 2000, and you're getting the outcome you want. Okay, so that's what I'm hoping that you have some understanding a couple of weeks from now as we practice it every day. All right, so don't sit there and go, oh, I can't do this. I don't expect you to do it right now. It took me months to figure out how to do this, and now it seems so simple, it's like mind-boggling. Okay, but it's not going to be that way for you until you figure it out, and I'm going to give you all the time in the world. And if you can figure that out by even the end of the semester, which I believe you can, because I've taught this to 6th graders, but if you take the time to keep thinking about it, you'll be fine. All right, okay, I just finished. That's all right, you come in now because I just ended this.